This video is sponsored by Brilliant. This is the oldest mechanical calculator in the world, invented by Wilhelm Schickard in 1623. He called it a calculating clock. It wasn't built for business or money, but for science, designed to help his close friend Johannes Kepler for the endless calculations behind planetary motion. Inspired by John Napier's recent invention, Napier's bones, Schickard combined gears and rotating cylinders to automate addition, subtraction, multiplication, and division. Tragically, the machine and its plans were destroyed in a fire, causing the invention to vanish from history for nearly 3 centuries, until it was rediscovered through surviving letters he had written to Kepler, quietly revealing that the age of mechanical computation began far earlier than anyone had imagined. This machine is composed of 3 main sections. The upper section, consisting of wooden rods, is used for multiplication and division. The middle section contains 6 dials and 6 rotary wheels and is used for addition and subtraction. The lower section, equipped with knobs and dials, is used for storing numbers. The machine is capable of performing arithmetic operations on numbers up to 6 digits. Let us add 10,543 and 20,342. First, the initial number is entered by rotating the wheels. The leftmost wheel is set to 3, followed by 4 on the second wheel, 5 on the third, 0 on the fourth, and 1 on the fifth. To add the second number, each wheel is rotated by the corresponding digit. Precise control of the rotation is achieved using a stylus. The stylus is inserted into the hole marked 2, and the wheel is rotated back to 0, resulting in a value of 5 on the dial. To add 4 on the second wheel, the stylus is placed in the hole marked 4 and rotated towards 0, producing a value of 8 on the dial. This procedure is repeated for the remaining wheels, yielding a result of 30,885. Now consider adding an additional number, 375. When 5 is added on the first wheel, the second wheel advances by 1 position, indicating a carry. Adding 7 to the second wheel generates another carry to the third wheel. Adding 3 to the third wheel produces a further carry to the fourth wheel. The final result is 31,260. For subtraction, the wheels are rotated in the opposite direction. Let us subtract 375. The first wheel is rotated backward by 5 steps by placing the stylus in the 0 position and rotating it to the 5th position. As a result of borrowing, the second wheel moves backward by 1 position. When 7 is subtracted from the second wheel, another borrow is transferred to the third wheel. Subtracting 3 from the third wheel causes a further borrow from the fourth wheel. The result returns to 30,885. How does this work? Addition and subtraction are fundamentally processes of counting. By marking the digits 0 through 9 on a rotating wheel, addition can be performed by rotating the wheel counterclockwise and subtraction by rotating it clockwise. Multiple wheels arranged in series allow large numbers to be processed. However, a method is required to transmit a carry when a wheel passes beyond 9. This is achieved by using gears. Each time the primary gear completes 1 full revolution, the adjacent gear must rotate by 1/10 of a revolution. This can be accomplished by using a single-tooth gear to drive a 10-tooth gear, thereby transmitting the carry. Because the driven gear rotates in the opposite direction, we need to add an intermediary gear so that both wheels rotate in the same direction. Subtraction with borrowing works the same way. When the single-tooth gear completes a full revolution in the opposite direction, the 10-tooth gear rotates by 1/10 of a turn, effectively reducing the adjacent digit by 1. By applying this gear arrangement across all wheels, a complete system for addition and subtraction is formed. A small bell is connected to the most significant wheel. Whenever a carry cannot be transferred further, the bell rings, indicating an overflow. Spring-loaded detent blocks are also added to the primary and intermediary gears. These hold each digit firmly in place and provide a tactile indication of each digit position during rotation. For multiplication, the column of sliders and the knobs at the top of the machine are used. Let us consider an example. 20,345 multiplied by 4. First, the top row is set to 20,345 by rotating the corresponding knobs. Next, the slider marked 4 is moved to the left. A row of numbers then becomes visible, representing the result of the multiplication. Each window displays two numbers separated by a diagonal line. The lower numbers represent the partial products, while the upper numbers represent the carries that must be added to the next column. Reading across the row gives us the digits 8, 1, 3, 8, and 0. The principle behind this method is straightforward. Each cylinder at the rear of the machine is wrapped with a multiplication table. When the sliders are opened, it becomes clear that these cylinders collectively form a complete multiplication table. Depending on the digit selected, the corresponding multiplication values from 2 through 9 are displayed. This method of multiplication was first introduced by John Napier around 1617 and is known as Napier's bones. Originally made from bone or ivory and later from wood, these devices enabled multiplication through addition alone. Napier is also the inventor of logarithms, which made large numerical calculations feasible long before the existence of mechanical calculators. Does this make you excited about math again? Probably not. Let's be honest. Numbers feel boring when they're just symbols on a page. But when you can actually play with them, move them around, and see what's really going on, math starts to feel very different. That's why I like Brilliant, the sponsor of this video. Brilliant doesn't teach by throwing formulas at you. Instead, you learn through small, interactive problems that help you build real intuition, step by step. Before you know it, things that once felt confusing just click. It also adapts to your level and lets you learn at your own pace. Brilliant helps you excel in math and computer science with visual, interactive problem-solving and personalized practice. Try Brilliant, and you might wonder why math was never taught like this in school. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Quasar-Ed, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Napier's bones are essentially a multiplication table divided into individual rods. To multiply 259 by 23, the rods for 2, 5, and 9 are arranged side by side. The row for 2 is read and recorded, then the row for 3 is read one place to the left, and the two results are added together. This process is just like manual multiplication, but eliminates the need to memorize multiplication tables. Schickard incorporated this principle into his calculator, replacing fixed rods with adjustable cylinders that could be set to any digit. By combining this system with the addition mechanism described earlier, large multiplications can be performed without writing down intermediate results. For example, to multiply 345 by 124, the upper knobs are set to 3, 4, and 5, and the sliders for 1, 2, and 4 are opened. The result from the slider marked 4 is first transferred to the adding mechanism. Next, the result from the slider marked 2 is added starting from the second wheel. Finally, the result from the slider marked 1 is added. The final sum is the product. If the result is needed for later operations, it can be stored by setting the lower knobs to the corresponding digits. These knobs are simply number wheels without any mechanism underneath. How can we do division? The procedure follows the same principles as long division. The goal is to find the largest multiple of the divisor that can be subtracted from the dividend at each step. First, the divisor is set on the top row using the upper knobs. Next, the wheels are set to the dividend so that subtraction can be carried out. Before subtracting, the appropriate multiplier must be determined. We begin by testing the middle slider, corresponding to 5, to check whether its value can be subtracted from the dividend. The resulting value is 120, which is subtractable. We then test slider 6, which gives us 144. This value exceeds the dividend and therefore cannot be subtracted. Thus, 5 is the largest valid multiplier. The value 120 is then subtracted from the dividend. This subtraction is applied to the most significant digits, since division proceeds from the highest place value of the quotient. The process is then repeated. Slider 5 is no longer subtractable, so slider 4 is tested. This produces 96, which can be subtracted and is therefore subtracted again from the current value. Next, slider 4 is no longer subtractable, so slider 3 is tested. This yields 72. After subtracting 72, the remainder becomes 0, and the quotient is 543. During the operation, the selected multipliers can be recorded in the register dials as they are determined. This ensures the correct order of digits in the quotient and avoids confusion during the calculation. Amazing, isn't it? The Schickard calculator may look simple, but it represents a huge idea. That calculation could be done by a machine. By combining gears with Napier's bones, Schickard took one of the very first steps toward mechanical computing, long before calculators became common or even practical. What makes this even more striking is how close we came to losing it forever. The machine was destroyed in a fire, never published, and forgotten for nearly 300 years, surviving only in a few letters sent to Kepler. Its story reminds us that progress isn't always loud or obvious, and that some of the most important ideas almost disappear before we even realize they existed. If you enjoy learning how things work, please subscribe to my channel. Thank you for watching, and I'll see you in the next video.